This video, I introduced the basic parametrization of plane curves. So as a quick definition, if x and y are given as functions f and g over some common interval I of t values, then the set of points x, y is the function values of f at t and the function values of g at t. Defined by these equations is called just a parametric curve. Also, it's called a planar curve, as the curve must lie in the xy plane. The equations are parametric equations for the curve. The variable t is called the parameter, and I is the parameter's interval. Continuing with our definitions, if I is a closed interval from a to b, then the point f of a, g of a is called the initial point of the curve, while the other point f of b, g of b is called the terminal point. If the interval is not closed but half closed, then we still have similar definitions for initial point and terminal point, depending upon on what n is the interval closed. If you have a curve and you give parametric equations and a parameter interval for the curve that generates that curve, we say that we have parametrized the curve. The equations and the interval together form a parametrization of the curve, and there is a point whose trace is the curve itself. Let's go ahead and try sketching one of these curves. So I'll make a brief table of values of x and y for given different t values, and I'll plot the points corresponding to them, and then sketch the curve that appears to be defined by the set of parametric equations x equals t squared and y equals t. Here there's no mention of the interval, so we assume that the interval is the largest possible interval so that you can still evaluate all the functions. In this case, that would be all real numbers. So here, making a single table for different t values where I picked integers going from -2 to 2, I found these corresponding x and y values. Then I could plot those points in increasing order of time. Now I'd like to know then what's the overall graph. To do so, I can't just continually plug in more t values to plot points. I have to guess at what the curve is. A common way to do that is to try to find a way to eliminate the parameter, to find an equation that relates x and y directly. Well, clearly, if y is t and x is t squared, you could then get that y squared is just x. And that's the equation of a parabola that is opening to the right. Notice that all the points are on this curve. Now there is a definite difference though than saying graph the equation x equals y squared and sketch this particular curve. See, when you sketch the curve, there's a feeling of time passing, so that you must be going in this direction. There's a feeling of motion that you travel along that curve as time passes. So the point x, y traces out that curve. But if you just draw the equation x equals y squared, that's just a bunch of points all at once. There's no feeling of time in that equation at all. Now don't be fooled. Just because this curve, as time passes, that this set of parametric equations traces out the entire parabola, does not mean that's always true. All I'm saying is that the parametric curve is a subset of the parabola x equals y squared. In this case, it is everything, but it doesn't have to be. Let's try that again. I'd like to sketch and identify the path traced out by this point x, y, given this set of parametric equations, and this time given this parameter's domain. So here, to do so, I'll go and eliminate the parameter. Notice that if I take that y as t, I can put the t right here to get x equals the square root of y. Rewriting the equation once, clearly y is the same as x squared. And we know what that graph looks like. So if I were to graph that equation, it would just be a parabola, which it should go through the origin, but I missed. It should go right through the origin right there, but I missed. And that's where this is the y-axis and this is the x-axis. But if you look at the parametric equations, notice you have a starting time value. That's when t is 0. When t is 0, we get the point that you see right here. But then also, as t increases, notice that the y must increase, and the x, being the square root of t, therefore must also increase. So I can only use the portion of the curve where both x and y are increasing. So if I were to graph this particular curve traced out by this point, it would start at the origin and then it would follow along only the right hand side of this parabola. That is the sketch of this curve, traced out by that point. Let's do that again. Another technique of going about finding a way to sketch the curve is to eliminate the parameter, but this time, notice the other examples I had that one of the variables was already t. Here, though, the best thing to do would be to just go and try to solve for some kind of common or related function of t. Notice if I take the first equation and write it as x equals a, I would get the cosine of t. And if I divide by a in the second one, I would get y divided by a is the sine of t. But I recall that the cosine squared of t plus the sine squared of t, that would have to equal 1. But the cosine is just x over a, and the sine is y over a. So I get x over a squared plus y over a squared. That equals 1. And if you just multiply both sides by a squared, you would get x squared plus y squared equals a squared. And that you all recognize as a circle. It's a circle. Now that means then that my path traced out by this point is always on the circle. I have to now figure out what portion of that circle is actually part of the path. Well, when t is 0, you get a corresponding x and y value, and when it's 0, you would get that x equals a times the cosine of 0. That would then be a for x. And if t is 0, y would be a times the sine of 0. That would be 0. So then, assuming that a is going to be positive here, that you would then this means that you would start at a point on the positive x-axis. If t would be then, let's say, pi over 2, you'll see that x is 0 and y is a. Now you're on the positive y-axis. If t is pi, you would then have negative a and 0. And then if I keep going around to 2 pi, you would get a and 0. So if I were to sketch this curve, it actually has to be the entire circle. It just starts at the point along the positive x-axis whose distance from the origin is a. It would then be the circle going all, well, maybe the circle should be a circle, going all the way around once. And in this case, notice it's going in the counterclockwise direction. Also, what's interesting is look, when you draw this curve, did you notice that for 2 different times you got the exact same point? That's kind of what's interesting about these curves when you describe them parametrically. You're associating a value of the parameter with a point. Well, you can associate a single point then to many such values. So if you think of it in terms of time, there's many times that you might come back to the exact same point. So these curves can self-intersect. They do not have to pass the vertical line test or the horizontal line test that's normally required of functions y in terms of x or x in terms of y. This gives us a lot more freedom to go and describe our curves. Let's try that one more time. Now, once again, what I'm going to do is I'm going to try to identify and sketch the path traced by this particular point given by this set of parametric equations. Now, in the previous slide, you saw a way to represent a circle traced out counterclockwise of radius a. There's obviously a reason why I'm showing you this one. Notice that for the first equation, you could solve for t. You could do the same for the second. If you do that, you would have x minus x naught over b. That would be t. But that would also be y minus y naught all over a. Now, if you take these two and divide them one by the other, or just take this expression and divide both sides by it, or take this expression both sides and divide by it, or do the same thing with these constants, you would get y minus y naught all over x minus x naught. That would then equal, you would get a over b. Or that's y minus y naught is equal to a over b times x minus x naught. And you recognize that as a line. It's just the equation of a line. It's the equation of a line whose slope is a over b. And notice in the equations, do you see how I put an A here? And that changes the y value. So this is the change in y. For the same reason, this b is being multiplied with t, so it's corresponding, it's changing this x value. So that's a change in x. So the slope here is literally the change in y over the change of x as expressed as two different constants. So that means then that this particular equation of a line is going to go through a point, that point being x naught comma y naught, and it will have a slope that is a over b. Now you have to be careful. Normally when you draw lines, you put arrows in both ends, but that's not what happens here. See, in this case, time is increasing. So if time is increasing, we don't know then which way we go on this line, because it depends upon, is this change of x here, is this positive or is it negative? If we assume if that b is positive, that means as t increases, the x increases and the orientation goes that way. But we don't know that without actually knowing what b is. If it's negative, the orientation would be the other direction. It will go from right to left in that case. This next example is a little bit more interesting. Here I have x and y are both given by functions of time, and I have that t, the parameter, is defined over the parametric interval from 1 to 4. Once again, I went to sketch and identify the path. It's a little more difficult because solving for t and plugging into the other equation is really difficult. It's actually better to notice that if you take these two equations, notice what happens if you add them. If you were to take these two variables and you add them, you get 2t. And if you take the two variables and you subtract them, you would get 2 over t. Well, that means that if you take x plus y and you were to multiply it by x minus y, the result is 2t times 2 over t. And that's just 4. So you get x squared minus y squared equals 4, which you may or may not remember is the equation of a hyperbola. It's a hyperbola that would be like this. It would be opening to the right, or it will be opening to the left. We just need to figure out which one. To do so, notice that no matter what t is, since t is positive, x is also always positive. So I only have this branch. And then since we start and end somewhere, it's probably a good idea just to make a little table of values to see where we begin and where we end. So this will then be your t values, your x values, and your y values. So t goes from 1 to 4. So if t is 1, x would be 2, y would be 0. We would start right here. If t is 4, then x would be 4.25, and the y value would be 3.75. I would have a 0.3, 4, and a smidge, 1, 2, 3, and a smidge. It'd be up here somewhere. And the curve would look like it starts here and goes there. And it is on the parabola, sorry, it's on the hyperbola defined by this equation. So it would look kind of like that. And it would go in this direction. Notice I'm not putting the arrows at the end, I'm putting them in the middle. Because if I put them at the end, it might be a little misleading. And that's it. That would be my sketch of the path. So to hammer home one of the major features here, when you have a parametrization, all you're doing is associating real numbers to points. In a way, you're kind of turning your path into a number line. It's just not straight anymore. And if you go and let the parameter increase at a stated rate, 1, 2, and 3, the distances between those points along the curve, well, they no longer need to be constant either. So it's kind of like creating a number line where the distance between numbers now has different distances. Now in the future though, the variables that correspond to the parametric variable, we often interpret them in certain ways. So if you see t values, we almost always think of them as time values. And if you have no context at all, we often will just think the parameter in terms of time, as it makes it easier to visualize. But if you see that the parametric variable is s, almost always s corresponds to a distance along the curve from a point on that curve. So it's a way to associate distance to a point. Now be very careful. If you have a certain curve in space, it has actually an infinite number of parametrizations. It's just different ways to associate numbers on that particular curve with points. So here I gave you two different parametrizations of the exact same thing. If I were to graph both of these, the graph would just be a line that would start at the origin and go to the point 1, 1, and the orientation would be the same. It's not the same parameterization because if I take the t-value of a half for the first parameterization, I would get the point a half a half. So in that case, in the first parameterization, t is a half corresponds to the point a half a half. But in the second parameterization, if I make s be a half, that parameterization associates a half with a fourth and a fourth. So they are different parameterizations. You get different associations with values and points, even though the curve and the orientation is exactly the same. But this freedom also leads to some other little bits of confusion, because if you have two sets of parametric equations, if you eliminate the parameter in each, you might get the exact same algebraic equation. But remember that the parametric curve determined or traced out by this set of parametric equations, it's only a subset of the graph when you eliminate the parameter. That means if you have two different sets of parametric equations that give you the exact same algebraic equation, when you eliminate the variable, they can still be different curves. So for example, in the first curve, this will give you the curve x squared plus y squared equals 1. So this graph, this particular path traced out by the point x comma y, will be a subset of this circle. Here though, if again you eliminate the parameter, you would get x squared plus y squared equals 1. So then whatever this graph is, it's a subset of this circle. But they don't have to be the same curve. Here, if t is 0, you would have, when t is 0, you would get an x and a y value. And if t is 0, the x would wind up being 0. The y would be negative 1. So this curve starts over on the negative x-axis. And then when you go to pi over 2, here the x value would then be 1. The y value would then be 0. You would then be at that point. Notice we're going in this direction. And if you go all the way up to pi, we'd be back over here. This curve is this part of the circle, and it's traced out that way. Notice it's not the whole circle. It was only this little bit, and it has a beginning and an end. On the other hand, here, if we again make a little table of points, you have your t, you have your x, and you have your y. Say t is 0, you would get that x is 1. And if x and the y value would then be 0. If the t value is 1, then the x now would be 0, and the y would be 1. That curve starts here and ends there and goes in this direction. Notice it's not the same graph. They're both subsets of the same circle, but they're different portions of it, and it's even different orientations. Now, a useful skill is, if I give you a curve, can you find a parameterization for that curve? So this is not a terribly easy skill. It takes a lot of practice. So a common way to begin such a thing is to start with a known parameterization and then use transformations. I've actually given you two different now parameterizations. One for the circle, x equals a times the cosine of t, and y equals a times the sine of t. That traces out a circle of radius a going counterclockwise and starting at the positive x-axis. And I also gave you the line, which was y minus y naught is equal to a times t, and x minus x naught equals b times t. That was the equation of the line of the slope AB starting at the point x naught, y naught. Assuming you have those two, you can find other parameterizations of other lines and of other circles with orientations as you want. For example, if I gave you two already existing, an existing parameterization of some curve, you could get a new parameterization by shifting the entire graph up, down, left, or right. To do so, all you do is you take the parameterizations and you add what you want to shift by. So if you want to shift the graph to the right, you would add to the x-coordinate x0, where x0 is some number. If you want to shift the graph down, then you would change the y value by adding to the y-coordinate, g of t, a negative y value. That would shift the whole graph down y units. You can also scale the graph by multiplying every single x value by a certain value and every single y value by some value, and that will stretch the graph by that much. So if a or b is larger than 1, you would then stretch the graph in that way. And if a or b are negative, you'd have to reflect it in the axes. You can also replace the parameter with negative t. The result is whatever the orientation was, it reverses it. So if you want to reverse the orientation in a circle for the parameterization I gave you, you could always replace every t with negative t. And now the circle would be traced out not counterclockwise, but clockwise. And finally, you can also time dilate. Just replace the t by t minus a, and that would associate different time values with those points. It essentially would shift all the times by a amount. You would still get the exact same graph. You would just change the possible input to t to be a more convenient time interval. I'll do two examples of doing so. So let's find a parametric equation and a parameter interval for the motion of a particle that traces out the line segment from 1, 1 to 2, 5. Well, to do this, I'll first find out then, since it's a line segment, I'll be using the line parameterization. So that'll be that y is equal to y naught plus a times t, and x will be x naught plus b times t. But I want to start at 1, 1 when t is 0. That means that x naught and y naught, that's already been defined. This has to be 1, that has to be 1. So now I know this must be 1 plus a times t, and this must be 1 plus b times t. Now I know, though, that this line is going to go from 1, 1 to 2, 5. But I'll get 2, 5, though, when t is 1. So let's use that fact. So when t is 1, I have to get that 1 plus a times 1. That is my new y value, which is 5. And 1 plus b has to be our x value, which is 2. Looking at those equations, you get that a has to be 4 and b must be 1. So the equations x equals 1 plus t and y equals 1 plus 4t over the interval from 0 to 1. That's to trace out the straight line segment going from 1, 1 to 2, 5 as the parameter goes from 0 to 1. So I'll do another example. Let's go ahead and try to find a parameterization for the circle that is traced out clockwise, whose radius is 2, and it's traced out the circle twice, and starts with the negative x-axis. So in order to do that particular problem, we'll start with a formula that we know gives a circle of at least radius 2. So then that would then be x is equal to the cosine of t, and y equals the sine of t. This gives you the circle of radius 1. To get a circle of radius 2, we'll just scale both of these by 2. That way, both the x and y directions are stretched out by a factor of 2. So that means that the radius now is 2 instead of being 1. But then I want to go clockwise, not counterclockwise. So this graph here goes counterclockwise. I'll replace the t with negative t. That will then give you x equals 2 times the cosine of negative t. And you have y equals 2 times the sine of negative t. This then reverses the direction. So this equation is 2 times the cosine of t, while this is negative the sine of t. This should now trace out the circle, still starting at the same point. We'll still starting at the point 2, 0. But now the graph is being traced out clockwise instead of counterclockwise. Well, think about that graph. This equation, these set of parametric equations, draws in this direction. It starts here. Now, eventually, it has to get to where I want to start. This should be then where t is pi. So when t is pi, I'm actually at this point. Well, then I want to go push time ahead a little bit. So the equations, x equals 2 times the cosine of t plus pi, and y equals -2 the sine of t plus pi. That should then give me a place, a parametrization, so that when t is 0, I should start here. You're welcome to check it out. Just go ahead and look what happens when t is 0 to see what x and y would be. If t is 0, I would get 2 times the cosine of pi. Cosine of pi is -1. That gives me then -2. And if t is 0, I then have y equals -2 times the sine of pi. But the sine of pi is 0, and I get -2, 0. The curve then starts here. Now that I have that, I know it's going to give me a circle, and I'm going to keep going this way. I just want to make sure that I trace out the circle twice. Well, if you look at these equations, you know the period of this function. The period of that function is 2 pi. So if I go from 0 to 2 pi, I would trace out this curve once. If I do from 0 to 4 pi, I would trace out this particular path twice. So if I use a parametrization from 0 to 4 pi, this would do it. This would do it. This will give you a parametrization of a circle of radius 2 that traces out the curve twice, clockwise, and starts at the -x-axis when t is 0. Now, finding parametrizations clearly seems a little intimidating, but there is a natural way to do it if you just want to get something, especially if you have one variable is a function of the other. These are called the natural parametrizations. All you do is you call the variable that is currently the independent variable for your function, you call that the parameter. You say x is, let's say, t. And then you could write down the dependent variable in terms of that independent one. There you go. This would give you a parameterization of this function. This is nice because then if you know the domain of your independent variable, that automatically gives you at least a parametric interval for your parameterization. Here, t can just be any old real number. And this parameterization will then, its trace, will trace out this entire curve. The advantage here is you're now associating time with points. While in this equation, there's no time really, so you don't really see that association. But sometimes, given an equation in x and y, using the natural parameterization, just to replace one variable with t, to get the other variable in, as a function of t, really isn't much better than just using the original function of x and y. So sometimes it's better to assign one of those variables to be a function of t and then use substitution to find the other. When you do so, really try to stick to functions that are strictly increasing or decreasing. Otherwise, your parameterization might retrace over part of the curve twice, and that might be confusing. For example, one such one would be, say x is a function of t. If that's true, just make sure that the range of x values and the range of t over the parameters interval you're going to use match. Otherwise, you won't get the curve you want. So look at the equation I have here. Now I could replace x with t and get a parameterization, but I noticed that I just don't feel like dealing with the square root anymore. So I could also instead say, let's say that x instead is really t squared, because in that case y being x to the 3/2 power, that would then be t squared to the 3/2 power. That would be t cubed. See, by doing that, I get rid of the square root in the parameterization. But the interval, let's see, so then x has to go from 0 to 4. This is a strictly increasing function. So it must go from the lower value to the upper value. So if x is going to be 0, then t must be 0. If x is going to be 4, then t must be 2. This set of parametric equations over this particular interval will then trace out the curve that we're interested in. And that gives you a very basic introduction to parametrizations of planar curves.